All right, so let's get started here with chapter 1. We're going to talk a little bit about basic idea of matter. Then towards the middle here of this chapter, we'll get into how to properly take measurements. And then we'll talk about significant figures and all that fun stuff as well. And then we will finish with density at the end. So let's take a look. So obviously chemistry is really the study of matter and really how matter changes, the characteristics of matter. Thank you. The transformations that it undergoes, the reactions that it takes. And matter really is anything that occupies space and has mass. So it's pretty much anything you can see or even maybe not see is considered matter. Plants, rocks, air, they're all really basically what represents matter. And when we talk about matter, there really is sort of 3 different states of matter that we come across. And oops, wrong way. Come back. There you go. Go this way. There we go. And the 3 states of matter are solid. And in the solid state, typically speaking, we have everybody pretty much very, very tight to one another. Everybody's packed in there pretty close to another. We then have the liquid state where everybody is still relatively close to one another, but there is a lot more room for everybody to sort of move around. That's why when we look at liquids, they are fluid, right? They're able to actually pass one another, which gives them that property of being fluid. And really the last state of matter is gas. And really in the gas state of matter, pretty much what we got going on is everybody has completely broken apart from one another. And as we'll talk about in a later chapter, they're basically flying around. They have a lot of energy as they sort of hit the walls of the container. That's what accounts for the pressure that we associate with gases. So a lot of what we deal with in chemistry does evolve around matter. It evolves around these different states and sort of what happens as matter goes from one state to the next. Speaking of that, there is the process where we go from solid to liquid. That is the process known as, what do you think? We take an ice cube out, it starts to, now it's the process of melting, right? Is that process there? We feel sad about our melted ice cube. We put it back in the freezer, right? And we take it from the liquid state back to the solid state. And that is the process of freezing. If we go from liquid to gas, that is the process of evaporation. Or vaporization. And if we go from gas back to liquid, that is the process of condensation, right? We can also have a spot there where we go directly from solids, skip the liquid part, we'll go way high up there, and come right back down to the gas. And that is what is known as sublimation. And we also could do the opposite of that. We actually can start with gas, skip the liquid, and head back to the solid state. And that is the process known as deposition. Like you're depositing something. Now, a couple of things that is important to sort of know or think about is, when these processes happen, for example, does melting and freezing, do they occur at the same temperature or different temperatures? They actually occur at the same temperature. So something like water at 0 degrees Celsius, that is when it freezes, and that's also when it melts as well. And really at 0 degrees Celsius, for example, in the water example, you pretty much have both states there at the same time. So you have kind of like ice crystals. So you got liquid water, you got some ice there. It's really not till you get below 0 degrees that you truly get full ice, if you will. Not till you get a little bit above 0 degrees that you actually get liquid water. And that's the normal melting point or freezing point for a substance, is basically when that occurs. Same thing here, this transition of evaporation or vaporization and condensation also occurs at the same temperature. And again, using water as an example, 100 degrees Celsius is when that occurs for water. And again, it's the same idea. At exactly 100 degrees Celsius, you essentially have both phases in equilibrium. So you have some liquid, you got some gas sort of happening exactly at 100 degrees Celsius. Not until you get a little bit above that 100 degrees Celsius that you do get it fully into the gas phase. And again, not until you get a little bit below the 100 degrees Celsius that you do get into the liquid phase. That is what is known as the normal boiling point for a particular substance, is basically when that occurs. Any questions on that there? Now, these transitions also, as we'll talk about as well in a later chapter, does revolve around energy. As I go from solid to liquid to gas, do I need to put energy kind of in to do that, or take energy out to do that? Energy needs to be put in. So if you think about your ice cube, right, it's sitting there, even though you may not do anything to it, it's picking up all the heat and energy from the surroundings, right? And that's why it starts to melt. You have a pot of liquid water, you put it on the cooktop, right? Start to boil it to make pasta or something like that, right? You're adding energy to do that. It starts to boil, which means it's going into the gas phase. That all revolves around energy absorbed. And those processes where we have energy absorbed is what is referred to as being endothermic. So an endothermic process is one where heat and energy is basically absorbed. And that transition as we go from solid to liquid to gas is a endothermic process. Now, the opposite is true. Obviously, if we're going in the opposite direction, if we go from gas to liquid to solid, we actually need to remove energy or release energy to do that. So if you think about everybody in the gas phase as they're flying around, if you remove energy, they're going to slow down. And as they slow down, what's going to happen is when they collide with each other, they're no longer going to have enough energy really to escape. So they're going to kind of drop into the liquid phase. You continue to remove energy from that situation. They're going to clump together even more and go into the solid phase. And these are all processes that energy is released. And those are all what are known as exothermic processes. So endothermic process, we'll talk a lot about as we go through the different chapters, has to do with energy and it being absorbed. Exothermic has to do with energy and it being released. Any questions on that there? Okay. So let's talk a little bit more specifically about each of these things. Solid, things in the solid state have a definite shape and a definite size. They're also said to be oftentimes rigid, which means it's really hard to change the shape of it, right? Like this desk over here, can't really just fold it in half or anything like that. It is definitely solid. You need a little bit of equipment there to help you do that. Same thing like bone, silver dollars, you know, our bones obviously are very solid, not easily change the shape of it unless you injure yourself. Liquid, on the other hand, has an indefinite shape, but a definite volume. Thank you. And what that means is liquid will typically take the shape of whatever container they're in. So really what that means is, for example, if you had 10 milliliters of water and you put that 10 milliliters of water into a bucket, like the trash can over there, it will take the shape of the trash can. If you take it out of the trash can and put it into like a silly straw, it will take the shape of the silly straw. Or you put it in a water bottle, it will take the shape of a water bottle. But regardless of what container you put it in, if you start with 10 milliliters of water and all you do is transfer it from one place to the next, you will end up with still 10 milliliters of water, unless you're a klutz and you spill it all over the place. But provided you don't do that, you should have the same amount of water. Gas, on the other hand, has an indefinite shape and an indefinite volume. Typically speaking, because gas molecules are basically flying around pretty much whatever container they're in, it is thought that they fill that container uniformly because they're just constantly moving around the actual container. And even so, as we'll talk about in the sort of the gas chapter, to a point where we actually don't even, in a lot of cases, worry about the actual volume of a gas. We more worry about sort of the volume of the container it's in, because they're flying around so much and filling that container uniformly. We don't have to worry about it. And obviously, as I mentioned earlier, as they are flying around and colliding, that is what's going to cause pressure that we associate with gases. Any questions on that? So let's talk a little bit about properties of matter. Properties are characteristics of substances that basically are used to identify that particular substance. There's really two types of properties that we come across. One is a physical property. And basically a physical property is a characteristic that you can basically observe about a substance without really changing what the substance is. So we can look at something and go, hey, it's blue, so that's the color. That's sort of a physical property. Things like odor as well. Main physical properties that we come across a lot in chemistry are the states, as we talked about just a second ago: solid, liquid, and gas. Things like melting points, boiling points, those are also considered physical type properties as well. And that's a little bit different than chemical properties. Chemical properties are really the characteristic of substances, basically kind of two things: how they undergo chemical change, and also how they can sometimes resist chemical change. So it's more has to do with the change that occurs in a substance as it creates a new substance. Things like rust and patina are actually examples of chemical changes. Sorry, chemical changes. And usually chemical changes pretty much is where we talk about when we do talk about the kind of the chemical properties. And usually chemical changes involve some type of chemical reaction to basically take place. So a main difference between sort of physical changes and chemical changes, which we're going to talk about here, I think on the next slide, is in a physical change, it's really a process where whatever you start with, and when you're done with that process, you basically still fundamentally have the exact same thing. So the substance did not change into anything new. Nothing new was formed. It may just appear a little bit different, as our example there of the ice cream, right? So we have ice cream and it melts. It's kind of sad, right? Especially if you're at a bottom ice cream there. But really, melted ice cream is still really ice cream. It's still the exact same thing. It's just in a different state. And really a key to sort of a physical change is, typically speaking, you could do some type of physical process where you could get back the original substance in most cases. Physical processes like freezing, melting, boiling, condensation, you could do those type of processes, filtering. So if we think about our melted ice cream, very simply, we could take our melted ice cream, throw it back in the freezer, right? And it will harden back up to sort of its original sort of shape, if you will. And we got obviously back our original thing. So really the physical change basically is what you start with and what you end with are fundamentally the same thing. So there's no fundamental change to any of the substances that basically occur. And that is 100% different than a chemical change. In a chemical change, what you start with and what you end with are fundamentally different things. So what you start with, what you end with, are definitely fundamentally different things. So patina like this, a little bit copper being oxidized in the air, forms that kind of greenish patina color. Rust, basically for rust, you start with iron and you start with some oxygen kind of separate from one another. And basically it comes together to form iron 3 oxide, which in this case, the iron and the oxygen are now sort of united together and you form something completely different than what you started with. You could take that rust, put it in a freezer, heat it up, I suppose, boil it. You'll never get the iron metal back. You'll never get the oxygen back by doing any of those physical type of processes. Try to filter it, it won't come back or anything like that. So the big deal between a chemical change and a physical change is really the opposite of what we see up there. The start and end are definitely different things. So we basically have different things that have been formed. And the other key to that is, again, you cannot get back your original substance by any type of physical means. Any questions on that? So let's talk a little bit about mixtures. Pure substances is a single kind of matter that basically cannot be separated into any other kind of matter by physical means. So a pure substance is pretty much what it sounds like. You got just like water, H2O by itself, for example. And nothing else is there. So you could have a pure substance of something like water. You could have a pure substance of something like copper atoms or something like that. That's just copper. It's basically one thing by itself, uncombined. Now, a mixture is when we take two or more pure substances and basically mix them together. The key, though, in a mixture, and is sometimes hard to visualize, is the actual stuff that you're mixing together. So the actual substances that you put together in a mixture, even though they may not appear that way when you look at the mixture, they actually do retain their identity. So they're able to retain their identity, even though you may look at a mixture and go, I don't see any part of it, or one part looks like it's gone, but they're able to really maintain their identity. So for example, if we have water, which is a pure substance, and if we take something like sodium chloride, which is salt, basically, that's also a pure substance. And if we put both of those guys together, we get a mixture basically of salt water, which is a mixture. So the salt water is a mixture, and obviously if you've seen salt water, I'm assuming before, when you look at salt water, it basically just looks like water, right? You no longer can really see the salt. So sometimes people think, well, obviously the salt's gone, it reacted, it did something, but it is actually still there. You just can't visually see it at that particular point in time. There's actually two different types of mixtures that we come across. One is a heterogeneous mixture. In a heterogeneous mixture, it basically contains different layers. So when you see a heterogeneous mixture, basically even after sufficient mixing, you can mix it all day. When you look at that mixture, you'll be able to actually see the different layers or phases, is sometimes referred to, when you look at it. Like chocolate chip cookies, right? That you will still see the chocolate chips. If you take some sand and water, right, you can mix that thing all day. That sand is never going to go anywhere. You will still be able to see the sand in the water. That is a heterogeneous mixture. You know, you put some metal in water, obviously, as well. You'll be able to see the metal, never going to dissolve or anything like that. Another type of mixture is a homogeneous mixture. A homogeneous mixture is one where with sufficient mixing, you basically see one phase. So everything looks the same throughout, like our salt water, for example, right? If we look at salt water, it just looks like water, but there is salt in there. You're not able to see it. It looks like one layer, and that is a homogeneous mixture. Also, if you take some sugar and water and put it together, you can mix it, and basically the sugar will dissolve in the water. Is again one where, as I said, when you mix it, you really don't see different layers. Everything looks the same. And those are really the two different. So our salt water there obviously is a homogeneous mixture. The sand and water is a heterogeneous mixture. One really important thing about mixtures is that no matter what type of mixture it is, whether it's a homogeneous mixture or a heterogeneous mixture, you can actually separate those guys out by physical means, and you'll be able to basically recover your original substances in their original form. So for example, we'll find somewhere I can scribble. We'll go here. So we'll go back this way maybe. So for example, if we look at our salt water, for example, or actually let's do sand and water. So if we do our sand and water, that is definitely, as we talked about, a heterogeneous mixture. And we could do a very simple procedure known as filtration, where we take like a filter paper and a funnel. You'll see why I failed the art here, filter. And we can actually filter this mixture here. We can pour it through. And if I pour this mixture through, what's going to get trapped on the filter paper? It is going to be the sand, right? So the sand will get trapped up here. And coming through will be the liquid water. And through that very simple procedure of filtration, we're able to separate out both components of that mixture. We got our sand. We could let our sand basically dry out, and obviously it'll be back in its original form. We obviously will have our liquid water. And by that simple physical process of filtration, we're able to retrieve back both components of our mixture. Now, let's take a look at the salt water here. I'll do it over here. So our salt water is a little bit different, right? When we look at our salt water, that is a homogeneous mixture. We really don't see the salt at all. So through a process where if we take our salt water and we create this sort of, we really want to collect everything, we could create this sort of enclosed environment where we have kind of two flasks on both sides. This is like a tube that connects it, and it's usually kept really cold in this process. And what we could do is essentially throw our salt water into one side. And basically we could do my wonderful drawing here of a Bunsen burner, also looks like a triangle. And we could start heating up that salt water. When I start to heat up the salt water, what's going to happen? Yeah, the water is going to start to evaporate, right? Which means it's going to go into the gas phase. And as it evaporates, it's got really nowhere to go. So it's going to be forced through this really cold tunnel, if you will. So when we have something in the gas phase and we cool it back down, it's going to go through, as we just talked about, condensation, right? And what will eventually happen is on this side, we will get that water basically collected on the right-hand side. As we continue to heat the left-hand side, eventually at some point, all the water is going to evaporate off, and you'll be left with probably not red, but more of a white salt probably there. But you'll be left with really just the salt that's left over on the left-hand side. And again, through this very simple process, physical process here of heating it, we have now separated out both parts of this mixture. We have our water on the right-hand side. We have our salt on the left-hand side. And again, we can let our salt kind of dry out and it'll be back like it was when we started. And really, the reason why this works is we're actually taking advantage of a physical property like boiling point. Because water will boil way, super way before salt will ever boil. Salt will never boil, by the way, it'll just start melting before it boils. So by taking advantage of the physical property of boiling point, we could separate out that water from the salt. And again, in this original mixture, when you look at it, you can't see anything. You can't see the salt there. It just looks like water. And we're able to actually get back both components. This process, by the way, is what's referred to as distillation. Any questions on that? You could do a very cheaper version of that, if you will. You put in like what's referred to as an evaporating dish. You heat it up, just let the water go out in the environment as steam. If you're not interested in collecting it, and you could separate it out pretty simpler that way as well. Any questions on that? So is making a mixture a physical change or a chemical change? That is both answers. So one of them should be right. So it is going to be a physical change, because in this particular process, right, we made salt water, but just by physical means, we were able to get back both components. So the key to a mixture is nobody really changes their identity. They still maintain their identity, which is your basic definition of a physical change. What you start with and what you end with is the same fundamental thing. It just may look different. So obviously salt water, the salt part looks different because we can't see it. The reason we can't see it is lots and lots of water molecules surround the salt, and it kind of goes away from visually be able to see it anymore. It doesn't actually go anywhere. So all mixtures are really physical changes because everybody's able to maintain their identity. Any questions on mixtures, how to separate them? Okay, then let's talk a little bit about other ways to classify matter. And an element is really a pure substance that cannot be broken back down any further. And really, when we look at an element, which are on the periodic table, you could think of elements as essentially like the alphabet. I think there's still 26 letters, give or take, I think, right? But there is lots and lots of different words we can make depending on the combination of the letters and how we put them together. And it's the same thing with our elements. There's different combinations of compounds and stuff that can be made depending on which elements come together or how many of each ones come together. But pretty much an element is as far back as you can go. There's kind of no going further than that. And the basic unit of an element is an atom. And an atom is really the basic unit of all elements. And as we'll talk about in a later chapter, they contain protons, neutrons, and electrons. So they contain all those guys in there, and that's the basic representation of really an element. Now, a compound, on the other hand, is a pure substance that is basically chemically joining two or more elements. So atoms of two or more elements coming together makes a compound. So like we see down there, table salt, which is sodium chloride, that is a combination of sodium and chloride or chlorine, and that is a compound. It's an ionic compound. Aluminum by itself is just an element. Now there is a common misconception or maybe misunderstanding of another word and how it differs from something like a compound, and that word is a molecule. And a molecule is two or more atoms together. So a molecule is more of a general definition of two or more atoms together. And it sometimes confuses people when they think of a molecule and a compound. They think, is it the same thing? And it can be, or it may not be, depending on the situation. So for example, when we're talking about elements, there are certain elements on the periodic table that when they come together, I'm sorry, I wouldn't say that wrong. There are certain elements on the periodic table that when they are uncombined and they are by themselves, they actually come as molecules. So for example, there are certain elements like H2, N2, O2, F2, Cl2, Br2, I2. These are what are referred to as elements. how hydrogen comes when it's all by itself is basically two atoms of hydrogen that are bound together. That is how hydrogen is by itself. Same thing with oxygen. Basically, two atoms of oxygen come together, and that is how it comes when it's by itself. Now, because H2, N2, O2, and all those things there listed, F2, Cl2, Br2, and I2 only contain atoms of the same element, they are all elements, even though they come as twos. So these are all elements. And they are also considered diatomic molecules. So they're also considered diatomic molecules. Diatomic, di meaning two, atomic meaning atom. So two atoms together make up a molecule. So something like H2, N2, O2, F2, and so forth there on that list I just wrote, those are all molecules because they meet the definition of a molecule, which is just simply two or more atoms together. It could be two or more atoms of the same element, it could be two or more atoms of different elements. If you're talking about a molecule, that is your basic definition. You need at least two or more atoms to come together. But each one of those are also elements because they only contain atoms of the same element. Would H2N2O2 be a compound? They cannot be a compound because they do not contain atoms of two different elements, right? So they don't contain atoms of two different elements. A compound would be something, in addition to what's on the screen there, like water. Water is a compound because it contains three atoms total, two hydrogen atoms and one oxygen atom, two different elements. So that meets the definition of a compound. Is water a molecule? Water is a molecule because it also meets the definition of two or more atoms together. So water is a compound, water is a molecule. Is water an element? Water is not an element because it is more than the same element there, two or more different elements together. So very often people get a little bit confused about molecules and compounds. So a molecule and a compound can be the same thing in terms of labeling something, but you definitely cannot have an element that's a compound because an element can only be the same element. Yeah, no, so a molecule, basic definition of a molecule is two or more atoms together. And again, like I said, it's really, you can think of it like a general definition. It's just basically that's all you have to meet is you got two or more atoms. Again, they can be the same element or different elements. Other questions? So here's a little flow chart of matter. Matter can be separated by physical means. If the answer is yes, then you probably have some type of mixture like we talked about. If the answer is no, then you have some type of pure substance. And if you can break it down even further, you have a compound. If you can't break it down even further, then you have an element. So for example, water, which is a compound, you can run an electrical current over it and break it down into its elements of hydrogen gas and oxygen gas. I guess I should do some balancing since this is chemistry. There we go. So this guy, which is a compound, can be broken down into its elements here. But again, once we get to hydrogen gas and oxygen gas, we cannot go any further. By the way, when I break down water into hydrogen gas and oxygen gas, is that a physical or a chemical change? Yeah, when I break down water into hydrogen gas and oxygen gas, like liquid water, is that a physical or a chemical change? It is a chemical change because you can take that, I wouldn't recommend it, but you can take the hydrogen gas and oxygen gas and do stuff to it, like physical stuff to it, you'll never get the water back. You actually have to do another chemical change to make the water. But yeah, we definitely have converted to something that is different than what we started with. All right, let's talk a little bit about the elements. There's about 117 elements. They obviously are listed here on the periodic table with their symbols. 88 or so of them occur naturally. Some are synthesized. A lot of the ones that are sort of man-made, if you will, are usually found down here in this part of it. These on this part of the periodic table with some weird symbols. That's typically where they put on the periodic table. Well, we haven't decided if we're going to really call that an element or not. And depending on when your periodic table was made, there may be boxes there, maybe no boxes in that little region. But that's usually like the spot where they were given a consideration to maybe put something in that spot. Now, a chemical symbol is basically written one of two ways. It is either a one-letter symbol or it is a two-letter symbol. The important part, though, is if it's a one-letter symbol, it should always be capitalized. And if it's a two-letter symbol, the first letter should be capitalized. The second one should not, so it should be lowercase. So elements obviously come from a wide variety of sources. They're sometimes just historical names or Latin names. They're sometimes named about where they were discovered, like Californium, Berkelium. They're named after scientists like Nobelium and all those kind of guys, Einsteinium. And so sometimes the symbols may be a little bit different than what you might think. Something like sodium, for example, capital N, lowercase a is sodium. Potassium is K. Iron is another one that maybe is a little different, is Fe. Copper is Cu. And again, you can see here, capital letter on the first one, lowercase on the second one, if it is to. Some other ones, lead, by the way, is Pb. Mercury is Hg. Yeah, that's mercury. Zinc, Zn. So it's really important, like I said, to sort of write them this way, because, if you wrote something like CO versus capital C, capital O, is there a difference in the meaning of these two things? Yeah, so the first one is cobalt, which is an element. Capital C, capital O is carbon monoxide, which is definitely very different than cobalt. So you may be, if you're somebody that capitalizes everything, you definitely don't want to do that when you're writing symbols. Otherwise, you may actually be writing something you're not meaning to write, and you might get it wrong. So always make sure you really do try to do that. Should you, and here's from your book, which you could clearly not see, but all the symbols and stuff like that on the periodic table. Should you learn them all? The answer is yeah, probably at some point you'll need to know. You definitely will need to know, the symbols and the elements when we get into the chapter about bonding and naming and all that stuff. Further to the left, we come across a lot, kind of from like lead this way, we do see a lot, and kind of in this region, like definitely this first row, and then down this way. So a lot of over in this area, we don't come across too much. The two bottom rows, not a lot, except for maybe uranium, which is U. But I would recommend taking some time to get some familiarity with the names and the element symbols, more so when we get to that chapter about naming. Just going to make the chapter go a lot easier for you. There's a lot of rules for naming, so if you're still fumbling around about what is a symbol for aluminum or something like that, you're going to run into a lot more problems. So as we continue, take some time, get some familiarity with it, and you'll probably be in good shape when we get to that chapter. As we sort of talked about a second ago, the atom really is the basic representation of elements. Pretty much all atoms of the elements will contain those protons, electrons, and neutrons. The one exception, as we'll talk about, is hydrogen. Hydrogen actually only has a proton and an electron. It does not have a neutron. But everybody else will have protons, electrons, and neutrons. And as we just talked about, again, a molecule is really just that basic definition of two or more atoms together. And again, they can be the same, which would mean that they are an element in that case, or they can be different elements, which means they will be a compound. They are held together in a compound one of two ways, which we'll talk about this semester. through either sharing electrons or through transferring electrons from one to the next, and kind of opposites attract is the two ways that sort of compounds are together. There are different ways that we sometimes classify molecules. Diatomic, as we just talked about earlier, is when you have basically two atoms together. Now, we talked about H2, for example, being diatomic. If we had something like carbon monoxide, which are two elements together, is that diatomic? It actually is diatomic because it also meets the definition of it. It is two or more atoms together. Oh, sorry, two atoms together, not more, two atoms together. In this case, it happens to be different ones. So if you're classifying something as a diatomic molecule, it doesn't necessarily have to be the same element. It just means that there's simply two atoms basically together in that case. Just like if we had HF, that also would be diatomic as well. Again, there's only two atoms basically involved. Triatomic, tri means three, so there's three atoms involved, you know, something like CO2, right? One carbon, two oxygens, something like water. Two hydrogens, one oxygen is triatomic. Tetra, by the way, is four. Penta is five. And you can kind of continue that pattern. Hexa is six. Hepta is seven. Octa is eight, and so forth. There's also homoatomic molecules. Homoatomic, much like a homogeneous mixture, means that everything is the same throughout. Homoatomic means we're dealing with all the same elements, basically. So H2 would be homoatomic, and it would also be diatomic molecule. Heteroatomic means like a heterogeneous mixture, you see different layers and stuff like that. So you see different elements involved. So these guys here, actually all these guys here, would be heteroatomic. They all basically have different elements involved. The top two would be diatomic, and obviously the CO2 there would be triatomic molecule in that particular case. Any questions on that there? Okay. Here's some pictures of it. These are a couple of chlorine. These are all homoatomic. That's sulfur at the end, and phosphorus in the middle. Each of those guys only contain the same element, which makes them homoatomic. These are all heteroatomic. They have the blue and the orange together, which are different elements involved. Any questions on atoms or anything like that? Now, a lot of times we do represent things with a chemical formula, and a chemical formula is used with the symbol for the element. And on the bottom right, we put how many of those atoms we have. So obviously, when we look at like H2O, which is on the bottom, 2 goes to the hydrogen. That means we have 2 atoms of hydrogen. Pretty much in chemistry, if you don't see a number there, it pretty much means 1. So if you don't see a number listed, it means 1. So basically what this says is we have 1 oxygen atom that is there in water. So in this guy here, we would have how many carbons? 9 hydrogens, and oxygens would be 4. This is aluminum sulfate. We would have how many aluminums? Sulfurs we would have? We would have 3. So we got parentheses. So we do need to kind of multiply this guy in. So it's basically 3 times 1, which would be 1 or 3. I did that math right. And this guy would also be multiplied in, which means we basically have 12 oxygens involved as well. Now, when we look at chemical formulas, sometimes chemical formulas gives us a lot of information about how things are connected, and sometimes they just give us straight up information about what's there. So if we look at this formula here, CH3COOH and C2H4O2, these two things are exactly the same. So if you count up the carbons in the first one, there's 2. Count up the hydrogens, there's 4. And if you count up the oxygens, there are 2. They both are really chemical formulas. The difference is this guy here gives you a little bit more information about how the thing's actually connected. And really, if you draw this, which by the way is acetic acid, which is like what you find in vinegar, it looks something like this. And here you can see CH3, CH3, CO, CO, and OH. So it gives you sort of the more structural aspect of how it's put together. And sometimes formulas will do that, but sometimes formulas are just like basic, here's what's there, no real information about how it's put together. Any questions on that there? All right, so we're going to kind of switch a little bit of gears here and then talk about measurements in chemistry. Now, measurements are really important in chemistry. And what makes a really good measurement is really two things. First off, if I just say, hey, I have 100, does anybody really know what I'm talking about? Nobody really knows what I'm talking about. I could have $100, which would be great. I could have 100 pennies, which I guess would still be good, I suppose, or 100 apples if you like apples. But whenever we give a measurement, you know, the number is really important, but almost more important is the unit that should go with it. It gives a person a frame of reference about what that number actually means, right? So clearly I say $100, you're gonna ask me to buy lunch. And if I say I have 100 pennies, maybe you would still ask me to buy a snack, I suppose. But you know, you have a reference for what that number really means. Now, examples of different types of measurements are mass, volume, length, time, temperature, pressure. And for the most part, there are two different sort of systems of measurements. There's sort of the English system that we use, and then pretty much everybody else in the world uses the metric system. So pretty much everybody uses metric system. Except for us, we use the English system. And believe it or not, you know, that obviously can cause some big problems if, you know, the world's smaller, we deal in different countries and stuff like that. So, you know, if we're going with the English system, other people are using the metric system, that's a lot of problem. So believe it or not, they had a conference in 1960 about weights and measures. Sounds like fun, not really. And they came up with sort of a standard system of measurement, especially in sciences. So you'll sometimes hear the SI unit. And that's the standard system of units, or the international system of standard units is the SI system. For the most part, let's be honest, it is basically the metric system is really based on. But for the most part, a lot of times in chemistry and science, you'll sometimes see the SI unit, and it really will be very similar, obviously, to the metric system. Also, why on signs, right, we also have things in kilometers. Why on your speedometer, right, when you look at it, it also tells you how fast you're going in kilometers per hour. Especially if you have like the older ones where you have the thing that goes that way. Digital, I think you could set it that way if you have a digital one, but the old ones would have kilometers per hour on it. So let's talk a little bit about some of the basic metric units. The meter is really the base unit for length. 1 meter is about 1.09 English yards. The gram is the basic unit for mass in the metric system. We definitely, in terms of length, use meters a lot in chemistry. We also use sort of the prefix versions like centimeters, millimeters, and kilometers a lot. Gram, again, like I said, is a very common unit of mass. We also use things like kilograms very commonly, as well as a very common unit of mass. Now, there is sort of a difference when we talk about mass and the term weight, and sometimes they are kind of used interchangeably. When we talk about weight, it actually does take into account the force of gravity. So for example, if we weigh ourselves here, we go to the moon to weigh ourselves, you will weigh differently because there's a different force of gravity, obviously, here than the moon. Technically speaking, your mass is sort of independent of the force of gravity. So typically in chemistry and most sciences, you know, when we go through the process of weighing something, we usually like to refer to it as the mass of the object. So you should get that, you know, sort of think about that. You don't really want to call it the weight, you know, sometimes people will mark it wrong, but we usually refer to it as the mass of the particular object. Now, in terms of volume, the liter is the base unit in the metric system. These are a couple of very common volume measurements that we come across: 1 liter and 1,000 milliliters. is equal to 1,000 milliliters. And 1 milliliter is equal to 1 cubic centimeter, which is the cm cubed there to the 3. How do we get something like a cubic centimeter? It is oftentimes very commonly used to figure out the volume of a solid. And we actually do like 3 length measurements. We take the length times the width times the height, for example, of a cube. And if we measure each of those in centimeters, you end up with centimeters times centimeters times centimeters, which gives you a cubic centimeter, which is a volume. So if you take like 3 length measurements and multiply them together, you typically are talking about a volume. Each of the individual measurements here are actually length measurements. So each of the individual measurements there are actually measuring length, but if you multiply them all together, you will get a volume. Also, again, that 1 milliliter is 1 cubic centimeter, and you sometimes see it as 1 cc, which also stands for a cubic centimeter. You maybe heard of cc's, you watch like a medical show, give the guy 5 cc's before he dies, right? So that is basically 5 milliliters. So it's very commonly used, like, you know, on syringes in the medical field, they call it cc's. And that's, again, just a cubic centimeter, which is, again, the same thing as a milliliter. Any questions on that? Now, in the metric system, we oftentimes will change sort of the meaning of some of these values so that we do not get a lot of zeros to deal with in calculations and stuff like that. So very common, you'll come across a table such as this, and very common people will do this table wrong or use what's on the table incorrectly. So for example, if we look at kilo, there, it is equal to 10 to the 3. So kilo prefix means 10 to the 3. By the way, 10 to the 3 is scientific notation. It is 1 times 10 to the 3, yeah, or 1,000 basically is what that means. So what that means is, for example, is if I wanted to do kilograms to grams, the base unit here is, what is the base unit there? That is grams, right? Grams is really the base unit. Kilograms is the prefix unit. So when we look on this table, when it says 10 to the 3, what that means is in 1 kilogram, there is 10 to the 3 grams. And it's a very common one that people will reverse that and go, there's like 10 to the 3 kilograms in a gram. So when you look at this table, what you see in that last column, 10 to the 6, 10 to the minus 1, whatever it may be, that is how much there is in the base unit to one of the prefix units. Doesn't matter what the base unit is, it doesn't. It works the same. If this was 1 kilometer, it would be 10 to the 3 meters. Same deal. This was 1 kiloliter, that would be 10 to the 3 liters. So it doesn't really matter the base unit, but what does matter is it's one of the prefix units to whatever that number is of the base unit. So if I looked at, for example, centi, which is here, centi is 10 to the minus 2. So that would mean if I did like centimeters to meters, where would the 10 to the minus 2 go to? It would go to meters. So what it means is in 1 centimeter, there is 10 to the minus 2 meters, or 0.01 meters that are involved. So that's a very super common error that people make all the time, is they reverse those numbers. So keep that in mind as you do it, and you use this table. Make sure that you are using it correctly. Any questions on that there? So as I showed us a second ago, if you took something like a cube and you take something that is the volume would be the length cubed, that gives us our cubic centimeters, which is the same thing as a milliliter. So let's talk a little bit about exact numbers and inexact numbers. So exact numbers have a value that really has no uncertainty in it. It's known exactly. So in chemistry, basically we come across exact numbers in two places. So for example, if I had, calculators up here on the desk, I'm not going to do any type of chemistry experiment or experiment to figure out how many I have. I'm simply just going to count how many calculators are there. And that's one way that we get an exact number, is some type of number that basically was achieved by counting. More commonly, how we come across sort of exact numbers in chemistry is by definition. So like 1 inch is, 12 inches is 1 foot. 1 inch, 2.54 centimeters. These are what are referred to as equalities. Equalities are basically two values that are in different units but represent the same amount, right? So if you have an inch, that is the same length as 2.54 centimeters. They represent the same amount or quantity of the measurement, but they're on different units. The deal with exact numbers is, technically speaking, in terms of significant figures, as we'll talk about, you essentially could have as many significant figures as you want. And the good thing about exact numbers is, if we come across them in calculations, as we'll talk about, you don't have to worry about them. You can kind of ignore them in terms of significant figures for your answers. And the other type of number that we come across is an inexact number, and that has some degree of uncertainty associated with it. And that's pretty much every measurement you take. So every measurement that you take will have some degree of uncertainty associated with it. The degree of uncertainty will depend on the piece of equipment that you're sort of using. And when we do take a measurement, there are certain rules that we follow when we do take the measurement. So let's take a look at, if we had something like, let's do, call that 2. All right, so that first big line is 1, that last line there is 2, and we'll call these centimeters. And let's just say we had something we want to measure to about there. All right, so when we look at a scale, there's really 2 things that you always want to do when you look at a scale, and that is to figure out basically 2 things. You want to figure out, what does the big markings represent? So in this case, the 2 big markings is, I have 1 centimeter on the left, and then we're stopping here at 2 centimeters. So between the big markings, it represents 1 centimeter, right? Between those 2, there are a certain number of smaller markings or dashes. So after the 1 is where we will start counting, which is right there. We'll start counting there. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 when we get to there. So there are 10 markings going across between the 2. That means in this case, each small marking represents how much? Yeah, each small marking does represent 0.1 centimeters, right? The first mark after 1 would be 1.1, right? 1.2, all the way up to 2. So whenever we take a measurement, no matter who's looking at it, there should always be certain numbers that everybody should agree upon. So if we look at my drawing here, this is 1.1, that's 1.2, that's 1.3, that's 1.4, that's 1.5. Next one is 1.6. So everybody should agree it is at least 1.5. These are sometimes referred to as the certain numbers. Now, even in my drawing here, it's not exactly on that 1.6 number. It's maybe a little shy of it. And that's where sort of the uncertainty comes into play. I may look at it and go, I think it's almost there. I think it's about 9. And obviously I would record centimeters. Somebody else may look at it and go, I don't know, it looks maybe more like a 7 or an 8, maybe it's not that close to the marking and stuff like that. And that is where the uncertainty comes into place. And this number here is what we call our first uncertain number. So that is our first uncertain number over there. And whenever we take a measurement, it is always custom to record all the certain numbers that nobody should disagree upon, and that first uncertain number. And technically, when you do that, you record all the certain numbers plus that uncertain number. That really is what we call significant figures. That would mean in this particular case, that measurement would have how many significant figures? Yeah, it would have 3 significant figures. The 1, the 5, and the 9 would all be significant. And basically what that measurement says is, I think it's 1.59. You know, I think it's this number. But maybe it's like 1.6. Oh, maybe it's 1.58. You know, it's somewhere in that region where that is the uncertainty. Typically speaking, it's plus or minus 1 of that sort of uncertain number. And, you know, if you do look at our drawing there, it is right about in that area, right? That's sort of where the uncertainty really does lie. Any questions on that there? Now, when we look at something, for example, let's say we're doing something like a graduated cylinder here, and we're taking a reading of a liquid. By the way, when we take a reading of a liquid, you should always see the curvature of the liquid, right? And that is what is known as the meniscus. And it curves because really the attraction between the liquid and the glass is stronger than the attraction between the liquid in itself. And what ends up happening is the side of the liquid starts to ride up the glass, and you get this kind of curvature. When we take a reading at the meniscus, it should always be from the bottom of the meniscus. So you should always read from the bottom of the meniscus, because if we didn't have the size rising and they stayed where they were, that's basically where the volume would actually be. So we would do the same thing here. We'll call this a graduated cylinder, and this is milliliters. We have 20 and 30, which means our big markings here are 10 milliliters. There are 10 markings between 10 and 30, or 20 and 30. That means each marking represents how much here for the small? Yeah, each one represents 1 milliliter. So if we were to look at my meniscus here, go there. We should at least be 21, right? 22, 23, 24, and 25, I believe, is above it. So it's not exactly 25, it's not exactly 24, but everybody should agree at least is 24. Again, here, this is where the estimate has to come in. Maybe I think it's right in the middle between 24 and 25, and I would record 24.5 with the 2 and the 4 being my certain numbers, the 5 being my uncertain number, or my first uncertain number. This would have how many sig figs? It would also have 3 sig figs in this case. And basically what we're saying is, I think it's 24.5, but maybe it's like 24.6, maybe it's like 24.4. And if you look at our drawing, you know, that really does sort of look correct. What we typically see is you could typically take the reading to one more place to the right of the smallest marking. The smallest marking here was 1 milliliter. We were able to go one more place to the right. In the previous one, the smallest marking was the 0.1. We were able to go one more place to the right of it. Is that always the case? It is not, but in most cases, you go one more place to the right of the smallest marking. Any questions on that there? Okay, we will lay it up there.